Hi everyone, this is our ECE 3710 final project presentation. We're group 2 and we're excited to show you what we made. We made a balancing ball game. The user controls the platform that the ball balances on with a joystick. The point of the game is to try to keep the ball balanced for as long as possible. Here's the overall design of our game. The CPU controls everything. It displays the highest score to a VGA. It processes data coming in from the Arduino, which receives its data from the joystick. So the user controls the joystick. The position is sent to the Arduino, which is then sent to the CPU, processed and mapped for what it wants to be, the position it wants to give to the motors, sent back to the Arduino, and that is mapped to the motors. Here is all of the hardware we designed for this class. The CPU is controlled by a finite state machine, and that basically controls everything. Where we really differed from the design we studied in class was in the program counter. When we decide to do a jump, we have that coming from our dest from the reg file. Furthermore, we had to design a hardware serial communication from the Arduino to the CPU. You used a UART module. There were some quirks about this, like the incoming data was only 8 bits, so we had to sign extend it to 16 bits before putting it into the reg file. Each of the two incoming coordinates, the X coordinate and the Y coordinate, are mapped to specific registers, R14 and R15. So every time they come into those specific registers, yeah, that's
All right, so for our UART module, that's to communicate with the Arduino. Like Tony said, we have a asynchronous setup with a 9600 hertz serial communication. We used one of the standard serial protocols, which is 1 start bit, 8 data bits, and 1 stop bit. Our UART is application specific, meaning that it's really designed to work for our setup. So basically how ours is specific is when we want to get data from the joystick, the X and Y positions, we will actually do a transmit to the Arduino, and we'll send it. For us, we have an initializing number, we call it, it's A5. So with our Arduino code, once we get that A5 value, that's when we'll actually send the X and Y position to the FPGA from the Arduino. And then other than that, the TX transmissions for our UART are pretty standard. And yeah.
So we have an assembler / compiler set up to generate code for our CPU. We have 2 separate files. One called our compiler will parse all of the assembly code, and it also supports if statements and comments. So it turns the if statements into the assembly code, removes all white space, and converts everything into the assembly instructions. So then the assembler can convert that neatly into machine code. Then we have all the standard instructions, control flow, arithmetic instructions, but then we also have instructions specific for communicating with our UART module and the VGA, as well as we have the capability to load values directly into memory. This is useful if we need to always jump a certain value and we know that ahead of time. And we use our compiler through the command line. So we put all of our assembly code in whatever file we want. In this case, it's called input, and then it'll print the machine code to whatever file we specify, which in this case is output, and then we'll load output into the VRAM in our CPU. So our actual software, it will read registers from the register file that Tony mentioned earlier, and those values come from the UART. So we take those joystick values, and then we need to compute the motor values given by the joystick. The joystick has a greater range than the motor is. So we need to remap the joystick values to the motor values. And we do this by using a combination of shifts and adds instead of multiplication and division, since shifting is equivalent to multiplying by 2 to a power. And then once we compute these values, we return it back to the UART.
So the VGA is a simple individual module that we attached on the side. We made this decision due to the static nature of our glyphs and the fact that they performed a simple just counting task. And so we didn't believe that there was the necessity to bring the CPU directly into manipulating the locations and the speeds. And so to do this, we integrated a basic timer function into the VGA module, which would count up, and then it had a high score capture, which would record the high score into a register. And then we used an algorithm called Dibble Dabble to break apart this binary count into individual digits, which we could display as the score. And then that was used to determine which glyph would be displayed at which time, giving us the time that you see on the screen. So this bypassed any use of memory, anything to do with the CPU directly, but it was controlled through 2 control lines coming from the CPU, which were a reset and enable, which would reset the counter, and it would also enable us to start and stop the counter without resetting. And then when you do a reset, if the current score is higher than the saved high score, it will update the saved high score in the registers. And then we stored our glyphs in a separate ROM file away from the memory to simplify access.
Got our final project built here. We got it working. So this is the joystick controlling the board here. The joystick inputs are going into the Arduino, where we send it serially to the FPGA. We have a UART module in there that receives the data, and our CPU processes and maps those coordinates from the joystick and then sends it back through our UART to the Arduino, where the Arduino writes to the servo motors and moves it. And then we have our VGA over here, and that's controlled by the FPGA switch. If you want to demonstrate that.
So the observer can start the score, pause it, and then reset it, and it'll record the high score on the bottom.
And then we'll show a demo of the game. Oh.